Solving logarithmic equations with multiple logarithms. All right, in the previous video, we talked about solving logarithmic equations that contain only one logarithm. We went over some information here. It's important information, but in case you didn't watch that video, the big important things were if we have a logarithm equal to another logarithm of the same base, then we could actually just say that the insides are equal to one another. We proved that. The other big thing we talked about is that with logarithmic equations, we always have to check our answers in the original equation to look for domain issues. There is the very real possibility of us doing every single bit of math correctly, but ending up with an answer that doesn't work. That's part of the process. So part of logarithmic equations is knowing we have to check our answers for domain issues every single time. There are two different ways that logarithmic equations get solved. We have our type A problems and our type B problems. Type A problems are going to happen when the original equation has terms that aren't logs. If you only have one log to begin with, then it's going to be a type A problem, but there are also type A problems that contain multiple logs. So if there is a term in your original equation that's just a single number, you have a +7 somewhere by itself outside of a log, you're looking at a type A, and we'll see more of that in a moment. Type B is for equations where all terms are logs to begin with, in which case we want to combine them together to get something like this, where we have log base b of something equals log base b of something, and then we can just set those insides equal to one another. So that would be something like log base 3 of 7x is equal to log base 3 of 14. Log equals log. We could take those insides and set them equal to one another. So we would have 7x equal to 14, and we would solve for x. So you're going to see both types of problems. Either problem, you have to check your answers for. Type A is loop-de-loo, type B is insides equal. Let's do some. All right, solve for x, give an exact answer. If there's no answer, write no solution. I could go through this entire page. I could go through all 2 pages right now and tell you if it's a type A or a type B. And maybe we will. Let's do it. Let's just look at them and decide if we're doing a loop-de-loo or insides equal. I'm looking at this guy. There's a log on both sides. There are no freestanding numbers. This is going to be setting insides equal. This is a type B. Type B. Insides equal. This next one. You see this freestanding 1 right here? This 1 that's not inside of a logarithm? Yes, we have logs on both sides, which is cool, but we also have this 1 standing out here making us nervous. So this 1 ruins everything for us. We cannot say it's a type B problem. Because of this 1, this is going to end up being a type A problem. And you'll see how we deal with it when we get there. But type A, this is loop-de-loo. Let's use, I don't know, 3. This guy down here, freestanding number right here. Logarithms on both sides, but that's not the issue. It's this freestanding number that makes it a type A problem. We're going to have to do a loop-de-loo. This guy right here, freestanding number. This 1 right here is a freestanding number. That's going to mean we are type A, loop-de-loo. Here, 3 different logarithms, but notice that there's not a term that's outside of a logarithm. Everything is in a logarithm. This is going to be a type B problem. There are no freestanding numbers, so we're going to end up doing insides equal. And I think this type of identification process is really, really important. Knowing how you're going to attack a problem before even starting it, really helpful. This guy right down here, Same idea as the previous one. We have all logarithms. Everything is inside of a log. So this is going to be type B problem. And that's all of them. So let's do them. Let's do them. So here we have two logarithms that equal to one another. Their bases are the same. So I can take the insides and set them equal. So we have 5x minus 6 is equal to 17. If I add 6 to both sides, I'm going to get 23. 5x equals 23. Dividing both sides by 5, I get x equals 23 over 5. I need to check that I can plug this number into this logarithm. So the only inside portion I have is 5x minus 6. So I'm only plugging it in to the inside portion. I don't really care to check my answer, although checking your answer is a good idea. All I care to see is if this makes a negative on the inside, because if I plug this in and it makes a negative on the inside, then there's no solution at all. So that's what I'm checking. Can I plug it into the logarithm? My x is 23 over 5. So we have 5 times 23 over 5 minus 6. This ends up being 23 minus 6, which is 17. Yeah, 17, which is a positive number, so we're good. I'm not looking for any particular number, just a positive one. Cool. This one. All right. I say it's a type A. I say it's a loop-de-loop. But you might look at this and say, I don't understand. How could that possibly be a loop-de-loop when there is no loop-de-loop? There's no loop to do. Well, my friend, what we're going to do is we're going to move this logarithm over to the other side. And then we are going to combine them together using our log rules. So we have log base 4 of x minus 3 plus log base 4 of x minus 6 is equal to 1. Remember, if you have two logs being added together on the outside, that turns to multiplication on the inside. So we have x minus 3 times x minus 6 on the inside. And now it's time to loop-de-loop because we have log equals a number. That's what this is saying. Make it into log equals a number. So we're starting at the base, across the equals, back again. We get 4 raised to the first power is equal to x minus 3 times x minus 6. This is also a quadratic equation. You cannot set these factors equal to 4 and solve it and expect anything good to happen. You're thinking of the zero product rule if that's something you're thinking. The zero product rule only works when one side is 0. The reason we were able to, where is that one quadratic? Oh, it was in the old video. The reason we were able to factor this and set each of these factors equal to 0 to find 6 and negative 2 is because one side was already 0. This was from our previous video, by the way. So back to this video. We're going to have to FOIL, move the 4 over, and then refactor. For my own sanity, I'm going to be putting this on the left side and this on the right side. If you FOIL this out, you're going to get x squared minus 9x plus 18 equal to 4 to the first power is 4. Subtracting 4, on both sides, 18 minus 4 is 14. So we have x squared minus 9x plus 14 equal to 0. This factors into x minus 7 times x minus 2. In a previous video, I said if you are uncomfortable with this factoring, gotta refresh on it. You really, really gotta refresh on it, especially going into the final. You don't want to be rusty on your factoring. Brush up on it. If this is uncomfortable, go brush up on factoring quadratics. All right, we get 7 and we get 2. We're going to have to check these in our original equation. There's 2 different factors we have to worry about. All right, so for x equals 7, we have the x minus 3 term, right? We have 7 minus 3, and that gives us 4, which is a positive number. Plugging 7 into x minus 6. 7 minus 6 is equal to 1, positive number. Right? This was from x minus 3, x minus 6. Checking the next one, 2. 2 minus 3, plugging it into this first factor here, that's -1, and we cannot have a negative on the inside. It also fails over here, but we didn't even need to go that far. No negatives inside of log. So if you were to plug 2 into this entire equation, you would get negatives inside of logs, and we can't have that. So number 2, not an answer, but 7 sure is. So we will keep him, and he is our only answer. Bam. Let's look at another one. This, again, is a type A because we have this freestanding 3 here. So I'm going to need to combine my logs together before I can do my loop-de-loo. So I have log base 2 of x plus 4 minus log base 2 of x minus 3 equal to 3. Subtraction on the outside of our logarithms turns into division on the inside. So we have log base 2 of x plus 4, all divided by x minus 3, setting that equal to 3. We now have log equals a number, so we'll do our loop-de-loo. Start at the base, across the equals, and back again, giving us 2 cubed equal to x plus 4 all over x minus 3. Two cubed is 8. So we have 8 equals x plus 4 divided by, you know what? I'm going to move this. I'm going to do this the lazy way and just replace this with 8. 8. We want to get this x minus 3 out of the denominator so that we can continue solving for x. So we're going to multiply both sides by x minus 3. On this side, we have 8 times x minus 3. If I distribute, I get 8x minus 24 is equal to, on the other side, we have x plus 4. If I subtract x on both sides, I'm going to get 7x minus 24 equal to 4. And if I add 24 on both sides, I get 7x equals 28. Dividing both sides by 7, I get x equal to 4. Right. You could write this down. Maybe I should. Maybe I shouldn't be lazy because I'm feeling like I might be lazy right now. You can just plug it in, right? 4 plus 4 is 8, good. 4 minus 3 is 1, good. You're good. That's your answer. But, you know, if I'm going to be a good teacher and set a good example, I suppose I will write it all out. It's good for us, right? So we're checking our answer, x equals 4, in the two different factors. So we have x plus 4 as a factor. We have x minus 3 as a factor. 4 plus 4 is 8. We're good. 4 minus 3 is 1. We're good. Bam. All right. Let's do more. There's 3 more I'm going to do, and that's it for this logarithm video. All right. This is the type of A. It's a loop-de-loo, and it's all because of this 1. So we're going to combine these guys together on the left-hand side and then loop-de-loo it. Addition on the outside will turn into multiplication on the inside. So we have 4 times x minus 2 on the inside equal to 1. This is where it's important to remember that ln of x is the same thing as log base e of x. So I can always replace ln with log base e, which I will be doing because I have to do a loop-de-loo here. So log base e, I'm also going to distribute my 4x minus 8 equal to 1. So I just distributed that guy. Time for our loop-de-loo. Start at the base, across the equals, back again. We have e raised to the first power equal to 4x minus 8. I am solving for x here. I'm going to go ahead and, I'm really tempted to move the e to this other side here because I like my x's on my left, but I also don't want to confuse anyone because the loop-de-loo happened. So I'm adding 8 to both sides. I get e plus 8 is equal to 4x. To get x completely by itself, I will need to divide both sides by 4. This gives me x equals e plus 8 all divided by 4. If I plug in e plus 8 all divided by 4 to my calculator, e plus 8 divided by 4 into my calculator, this number is approximately 2.68-ish. 2.68. If you plug it in, 2.68 minus 2 is a positive number. So we're good. That answer works. Positive number. These last two are going to be insides equal type of problems, which means we are combining logs together, and then we are setting the insides equal. So we want it to be log equals log before we do anything. So here we have addition on the outside, so I'm going to turn that into multiplication on the inside. I'm going to put the 5 out front. 5 times x minus 4 is equal to log base 9 of x. It's log base 9 equals log base 9. I can take these insides and set them equal to one another. So 5x minus 4, not 5x minus 4, 5 times x minus 4 is equal to x. Distributing the 5, 5x minus 20 is equal to x. If I subtract 5x on both sides, I get negative 20 equal to x minus 5x is negative 4x. Dividing both sides by negative 4, 20 divided by negative 4 is 5. So I get x equals 5 as an answer. I'm now going to check in all of the factors. So there's x minus 4 that I have to plug it into, and I need to plug it into x. Those are the two different insides of logs that have x in them. So 5 minus 4, that is 1. That's a positive number. And then 5 itself is a positive number. So we're good. That works. 5 is our answer. Yay. Last one. Type B problem, because we have only logs. There are no freestanding numbers. I'm going to combine together the right-hand side, minus on the outside, division on the inside. So we have log of 6 is equal to log of x minus 2, all divided by 20, right? Numerator, denominator. We have log equals log, so I am good to set these guys equal to one another. 6 equals x minus 2, all divided by 20. To get x by itself, I will be multiplying both sides by 20. That will cancel out the denominator on the right-hand side. 6 times 20 is 120, equal to x minus 2. If I add 2 to both sides, you will get x equal to 122. There's only one place you need to check it, and it's right in there with x minus 2. Clearly that's going to work, but we are good studious students, and we will write everything down. So for 122 minus 2 is 120. That's a positive number for certain, and therefore that is our answer. All right, so there it is. Logarithmic equations with multiple logs. It just comes down to one of two types. Knowing which one you're going for is vital. It'll make everything so much easier. If you have questions, let me know. Send me an email. Otherwise, if you do have questions and you haven't watched video number 1, please do go back and watch video number 1. And then the rest of the videos are going to be about solving exponential equations. All right, I'll see you in those videos. Bye.